Okay, so here we are, section 10.2. So the topic of the day is not red, it should be in blue, is sequences versus series. In the last lecture we talked about a sequence which we said looked like this: 1, 5, 9, 13, ... The not so famous every other odd sequence. So it's a real simple next step to go to the corresponding series, which is 1 plus 5 plus 9 plus ... 13, etc. So in integral calculus, we talked a lot about adding up a bunch of little rectangles, or adding up a bunch of little shells or little disks to get some sum, and so that's what we're going to do here. So we will write this series as it relates to the sequence as a sequence of partial sums. Okay, what does that mean? We'll say that S sub 1, the first partial sum, really equals A sub 1, and that's it, which equals, in this case, 1, which still equals, in this case, 1. Alright, so how about S sub 2 is the second partial sum, which really is the sum of the first two terms in the sequence. So in this case it's 1 plus 5, and that equals 6. I told you guys this will be easier than calculus. S sub 3, you got it, A sub 1 plus A sub 2 plus A sub 3, which equals 1 plus 5 plus 9, which equals 15. Alright, so we can see where this is going. But now we're going to generalize it and say that S sub n, the nth partial sum, is the sum, and I don't know if you've seen this sigma notation, probably in a physics class for sure, but this notation means sum. And I'm going to go from k equals 1 to n, so I'm going to count up all the a sub n's all the way up here, and that's whatever that turns out to be. We don't know at this point. Alright, but we're talking about infinite series. Okay, so now if we look at the total sum, I'm not looking for the nth sum, but the total sum is the limit as n approaches infinity of all these partial sums. And that's really what the game is all about today. Now in this particular case, 1 plus 6 plus 15, you can see this is just going to keep getting bigger. Our sums will get bigger and bigger and bigger and bigger and bigger, and it's not really that cool. So let's look at a different example of a sum. I've got to unclip my notes here. I'll start a new page over here, and we're going to look at another type of sequence. Right, remember when we looked at the other day, this one here is an arithmetic sequence. There's a common difference. Well, perhaps in a previous class you learned that there is what's called a geometric sequence, which then corresponds with a geometric series. That would be something like example 1 plus 2 plus 4 plus 8 plus 16 plus ... Okay. Well, how about this one? Well, these keep getting bigger and bigger and bigger and bigger as well. So if we go to infinity, this is just going to get really big, really big. Another example. Well, you know what we could do is write this one out. Let's see if we can figure out how to write this one neatly. We could say that this is the sum from n equals 1 to infinity of, say, 2 to the n minus 1. Ooh, that's interesting. So we've got our first term. I know these go up by 2 every time, but the first term is 1, which is really 2 to the 0, so I've got to do this. Alternatively, I could have written it as this way. And we'll get more into notation in a little bit. I could say n equals 0 to infinity of 2 to the n. So if this confuses you, pause for a minute, look at these two and make sure they look the same. Here's another example. Now this one gets a little more interesting. How about 1 plus 1/2 plus 1/4 plus 1/8? And you can see where this one is going. This is a geometric series where n equals, or the common ratio, the ratio between each one is, so a sub 1 equals, in this case, 1, and the common ratio, r equals 1/2. All right. So that's a geometric series because instead of a common difference like there were over here, we're looking at a common ratio like there are here. So let's go to the next page and look at a interesting example. So the example I'm going to use to kind of get the concept across, I hope, let's say we've got a floor here and a wall, and over here you've got a little kid. The little kid's got a big head like little kids often do. Looks like that. And he's getting annoying, and you think you need to come up with something to entertain him. So you say, okay, I've got a challenge for you, little kid. I bet you can never make it to this wall. You can't walk over there. So you challenge him. You said, okay, the first time you can walk, you can go halfway to the wall. And the next time you do it, you can only go halfway to the wall. And the next time you do it, you can only go halfway to the wall. And the next time only halfway, and the next time only halfway, and the next time only halfway. Now, we've all done this before. Maybe you haven't. Maybe I'm just meaner to little kids than you are. But you and I both know that, well, if we do this, we always only go halfway. We can never make it to the wall. And the little kid says, of course I can make it to the wall. I can make it to the wall. Eventually I'm going to get there. And you say, no, you won't, because you can always go halfway. Well, this raises a really interesting question. Is, who's right? You or the little kid? Now, in the next 20 minutes or so, you might find out it wasn't who you thought. So, what are we really trying to do, right? We know that this is going to be the sum from n equals, let's say, 1 to infinity of 1 over 2 to the n, like that, right? So it's 1 over, and this is supposed to be a 2 here. Let's make that a little more 2-like so it doesn't look like a z. 1 over 2 to the n. So if we go all the way to infinity, what happens? All right. So we know that a sub 1 is going to equal 1/2, and then this common ratio is going to equal also 1/2. All right, but we knew this. We haven't learned anything yet. So the sum is going to equal 1/2 plus 1/4 plus 1/8. So for now, I can write this as S equals A sub 1. I'm just going to call it A. I'm going to say A equals A sub 1 here. Just, you'll see why in a sec. Plus some common ratio times A. In this case, it's 1/2. Plus the common ratio times this again, so it becomes R squared A plus R cubed A plus R fourth A. And that's going to go on and on and on and on. Oh, I ran out of room there. Let's cross this out. Start over. Didn't realize my eraser is pressure sensitive. kind of nice. Alright, so we know that the sum here, the sum, is going to equal the first term A plus the first term times the common ratio, so it's 1/2. 1/2 times 1/2 plus 1/2 times 1/2 times 1/2 plus 1/2 times 1/2 times 1/2 times 1/2, and this is going to go on for a long time, right? So what? You know, is this any easier than adding 1/2 plus 1/4 plus 1/8? Well, let's just for kicks, let's say we multiply both sides of this by r. So we have r times this sum. What are you doing, Dressler? Well, bear with me. So a will become a times r plus ar squared plus ar cubed. That's bad. For the sake of these notes, for those of you using pre-printed ones, I'll clean that up. AR cubed plus AR to the 4th plus etc., etc. Right? Well, what good did that do? Well, let's take a look. What if we were to take these two things, which we know are equal, and we subtract them? And so now I've got down here S minus RS equals, well, what does this equal? I gotta change color here, change color. So we realize that here this AR is going to cancel with this AR, and this AR squared is going to cancel this AR squared, and this AR cubed is going to cancel this AR cubed, and whatever is down here is going to cancel with whatever down here, and that goes on to infinity. So all we really have left here, all we have left is a sub 1, the original one. Well, that's kind of cool. Now if we do a little algebra, and I told you this is going to be about algebra, and I factor out an S, this becomes S times, S times 1 minus R equals, all I'm left with over on this side is A. And that leads me to believe that S equals A over 1 minus R. All right, so that was pretty cool. Now, if we apply this new formula, that we know that S equals A over 1 minus R, I can go over to this side, and I can say for this particular series, so the sum from n equals 1 to infinity of 1 over 2 to the n will equal, all right, a sub 1, which is just 1/2, over 1 minus the common ratio, which is also 1/2. And how does that pan out for me? That's 1/2 over 1 minus 1/2 is 1/2 equals 1. So who's right now, huh? The little kid is right. The little kid will get there. They just had to take an infinite number of increments to get there. So you just don't have to tell the little kid that next time you do this trick. All right, now I got to be honest with you. We're going to do a little heart-to-heart here. Heart, check this out. Red. Gratuitous use of color. I told you guys I'm going to start doing that more. Heart-to-heart. I lied. Over here I lied. Because when I do all these things, back on the left side here, A sub r's cancel, A r squareds cancel, A r cubes cancel, A r fourths. Well, whatever I'm left with on the end here is actually going to be, what is it going to be? A sub n. It'll be up here. No, down here I've got one left. I've got one more term that I didn't really account for. And so we'll call this, I'm going to modify this to say S equals, where is it here? Oh yeah, it's R minus RS equals A plus A sub infinity, right, which will be the last term. Infinity, the infinite, that's hard to do on a microphone, infinite term. So when can I say that I can neglect this? So the question is, with this term, can I really neglect this last term? And I can say only if R is less than 1. Only if my terms get smaller and smaller and smaller, like they do in this last example with walking towards the wall, can I neglect this. So this is a very important rule. In fact, that's so important I'm going to give it the red box award. Only if R is less than 1 will that work. All right. So let's look at another example. So we now have figured out that we can sum up a geometric series. So let's see if we can sum up another series. And this will be the example of what they call a telescoping series. The telescoping series. And what that looks like is the sum, again, will go from n equals 1 to infinity, and I'm going to say it's 1 over n times n plus 1. All right. So let's look at the first few terms. When n equals 1, that equals 1 over 1 times 2, which is 1/2. Plus when n equals 2, I just put these little 2's up here. 2 times 3 is 6. So 1/6. Plus when n equals 3, 3 times 3 plus 4 is 3 times 4 is 12. Okay, so it's 1 over 12. All right, I don't really know. I don't know what's going to happen when I add these up. What's going to happen? 1/2 plus 1/6 plus 1/12. Well, how about we rewrite this guy? And we write that guy as n equals 1 to infinity of... Anybody know what I'm going to do here? Can you make a guess? 1 over n minus 1 over n plus 1. Whoa, what's this? What's this? If that's not crystal clear what I did here, and I'll give you a hint, I did this exact thing. I did this. I'm going to put this in red. If this is not clear to you, go back and look at your partial fraction decomposition. I told you guys it's going to be algebra, and this is not calculus here. This is just partial fraction decomposition. That was just algebra to do that. So make a note of that if it's not clear. All right, so what if we expand this one? That is going to equal, well, the first term when n is 1, it's just 1 over 1 minus 1/2. All right, that works. And then I'm going to add to that 1 over 2 minus 1 over 3, which I know just from cooking that's 1/6, plus, let's make this a dot, 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 plus 1 over 3 minus 1 over 4. All right, and you can see where this goes. Well, what's going to happen to some of these terms here? Get out the old cancel pen. Negative 1/2 and positive 1/2, those are going to cancel. And then negative 1/3 and positive 1/3, those are going to cancel. Negative 1/4 and positive 1/4. So really what this winds up looking like is equals 1 minus dot 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 dot, I go all the way to the end here, 1 over n. Now the limit of this, so the limit as n goes to infinity of 1 minus 1 over n equals what? Think about that. N goes infinity, what happens to this guy here? That goes to 0, so that equals just 1. Now, why do they call this a telescoping series? Because it looks like the old-fashioned, the old pirate's telescope. It looks something like this, and then there's like a little, kind of a little bigger part that goes like this, and then if he's a really successful pirate and he's really pillaged some nice ships, maybe it's got another part that goes like this. And then, when he's done using his telescope, he just takes this and slides it that way, and then this and slides it that way. This is so in case you're wondering what this is, that's a telescope, like the old pirate's telescope. And so it collapses like that. Much less this does here. All we're left with is 1. All the middle stuff kind of disappears, and we're left with just the 2 ends. So telescoping series. So that equals 1. All right, so what? So I happen to pick a couple of winners here. So the geometric series with r's less than 1, and the telescoping series that boils down to nothing too. So wouldn't it be nice if I could tell if a series converges? The Christina question, does it converge? Christina, after Christina in the morning class, who always asks me, well, what does converge really mean? So for Christina, let's take a look. I think where do I have to go to get a file? I think I have to go here. Nope, I go here. So I want 10.2 we're working on, yep, and we'll say infinite series definition. Here we go. All right, so I think we've kind of covered this all right. So given a sequence of numbers a sub n, an expression of the form a sub 1 plus a sub 2 plus a sub 3 plus blah 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 a sub n is an infinite series. Okay, so there's the big difference between I'll do that in yellow. The infinite series is the sum here, where a sub n is the nth term. The sequence, blah 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 blah, so s sub 1 equals a sub 1, s sub 2, so these are the sequence of partial sums, is the sequence of partial sums of the series. Number s sub n being the nth partial sum, alright, we've been over that. If the sequence of partial sums converges to a limit L, right, we talked about that in the last lecture, we say that the series converges, and that its sum is L. In this case, we also write blah blah blah, the sum of all these little terms equals L. If the sequence of partial sums of the series does not converge, we say that the series diverges. So diverge doesn't necessarily mean it gets huge. Diverge just means it doesn't converge. And so I'm going to stick one more little detail in here. I hope I can fit this on the bottom. 10.2, so we're going to do Theorem 7. Stick that in there. Do I have room? Oh yeah, we'll squeeze that in there. Look at that. Perfect, like it was made to be there. So what does this say? Theorem 7. If the sum of a sub n converges, then a sub n goes to 0. Right? If the sum converges, we know that the individual terms must go to 0. Alright, well, let's take a look. The next example we're going to look at is called a harmonic series. And what that is, this series is defined as n equals 1 to infinity of 1 over n. Alright, easy enough. So that becomes 1 plus 1/2 plus 1/3 plus 1/4. Alright, so a sub n is going to 0. There's no doubt about that. Plus dot 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 dot. Plus 1 over n, which is going all the way to infinity. So this thing, does this converge? I wonder. Let's take a look. I'm going to rewrite this, give myself a little bit more room here, as 1 plus 1/2 plus, now here I'm going to mix things up a little bit, 1/3 plus 1/4. And if you don't understand why I'm doing this, that's okay, that's the point. And then I'm going to sum these together. I'm going to group these as 1/5 plus 1/6 plus 1/7 plus 1/8. And then I'm going to add this to another group like that. Now if you check what these are, this is 1, this is 1/2. This little group here is actually a little bit bigger, greater than 1/2. And this little group here, it took me a little longer to do it, but I could make this one bigger than 1/2 here. And this next one that actually goes from 1 over 9 to 1 over 16, that one actually is a little bit bigger than 1/2 as well. So I can keep grouping these together, and we'll talk about this more in the next section. I can keep grouping these together so I can always get a chunk bigger than 1/2. So if you try to tell me, well, I bet you can't get past 6, well, it's going to take me a while. I'm going to have to group a lot together, but I can keep putting chunks of 1/2 together, and I can get past 6. So we know that n is getting smaller, but the series, this harmonic series, diverges. All right, now, wait a minute, didn't I just tell you the opposite is true? Let's go back and take a look. I said that if the series converges, then a sub n must go to 0. Not the other way around. The opposite, the converse, somebody can check that for me, I think that might be called the converse, is not necessarily true. Just because a goes to 0, a sub n goes to 0, does not mean it converges, so we have to be very careful about that. Alright, so we need to throw in a few more tools here to put in our toolbox. So let's add a few more tools. And one more dot. Makes it look nicer. And so I'm going to add a couple tools in here. Sum rules, theorem-made sum rules. Alright, so let's take a look at these guys here. So the sum rule. If the sum of kind of two sequences like this, we can split that up into the sum of the first one plus the sum of the second one. Alright, good. The difference rule, the sum of this minus this, equals the sum of the difference of the sum. So the sum of the differences equals the difference of the sums, a minus b. Constant multiple rule, the sum of k, and where k has to be a constant here, of some series, is the constant times the sum of the series, equals ka. Now this should look awfully familiar because we really know that an integral, right, this little symbol here, which looks like an S for a reason, is related to this one here, which is another sum. This is big capital S for sigma, for sum, and this is S for sum. That Leibniz came up with that one. All right, I'm going to erase that so that doesn't confuse anybody. But just so you know that that was there, that these rules are the same as the integral rules for a reason. For a reason. So let's look at an example. Here's an example. And this example will be, find the sum of, let's see, 1 plus, oh, nope, I mean I can make that plus. I'm going to make that 1 minus, I thought we were summing, plus 1/4, minus 1/8, plus 1/16, minus 1/32, plus dot 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 dot. And we're going to have some minuses, pluses in there. We've got all sorts of crazy stuff going on. Well, let's take a look at this. Is this geometric? Well, the terms kind of go down like they're geometric, 1/4, 1/8. So the common ratio seems to be 1/2. But, well, let's see if we can write this out. I'm going to say this is the sum from 1 to infinity of, how can I get this thing to flip sides every time? Flip back and forth. 1 plus, negative, plus, negative, plus, negative. I'm going to say that's -1 to some power. I'm going to say this is n plus 1. I don't want that. N plus 1 over 2 to the n minus 1. Wow, I've got all sorts of pluses and minuses going on. Does this work? Let's take a look. So at first I'm saying -1 to the 1 plus 1 is -1 squared, so it's a +1, over 2 to the 1 minus 1 is 0, so that's just 1. Alright, so the first one works. Plus, because I'm summing, right, that means plus, -1 to the 2 plus 1, it's -1 to the 3. -1 to the 3, that's really -1, over 2 to the n minus 1. I'm at 2 right now, so that's 2 to 1, so that's 2. So that's negative, so that's really 1 minus 1/2. Oh yeah, this is looking alright. So then I've got 1, let's see, the next one should be plus 1. This is the third one. 3 plus 1 is 4, so that's an even power of -1. So that becomes a +1 over 2 to the, let's see, 1, 2, 3, 2 squared is 4th. Oh, yeah. So maybe we can write this as a geometric series where, so it's geometric, right? That's good. That makes us happy because we know how to sum those. We just need the first term. So a sub 1 equals 1, and the common ratio, this time, what is the common ratio? To get from here to here, and from here to here, it's really -1/2. So we know then that the sum must equal 1 over 1 minus -1/2 equals, well, that's 1 over 1 minus negative is plus, really, so 1 over 3/2. How do I do that? Flip that guy and multiply, right? So this equals 2/3. Alright, now this is interesting. This is interesting. We did this one with a little kid. Remember we were messing with a little kid? So this much of it, when it's positive, sums up to be exactly 1. And so now we've kind of added an extra term in here, so we would have expected it to get bigger. So 1 plus, we know that this would give us 1 if they're all positive, so it'd be 2. But really this one got quite a bit smaller than our little kid example. In this case, if you told the little kid, well, you can take half the way towards it, and then half the way back, and then half the way towards it, half the way back, then you'd never get there. So it's just interesting to see that this sum turns out to be a little less than 1. All right, even though we even started with 1. Okay, good. Let's move on to, let's do some more examples now. I'm just going to bang out a bunch of examples, and they'll give you a feel for how to get started on the homework. Another example. And this time I'm going to say, I'm going to take the sum from 1 to infinity. Notice I'm getting lazy here. I'm not writing the n equals. I'm just writing the 1. That's right. That's just kind of a shorthand. 7 over 6. I'm going to raise that to the k power. All right, k. K, what about n? Well, it doesn't matter. It just, as long as by putting a k here, I'm implying that k goes from 1 to infinity. So a good place to start usually is to write out these 7 over 6 plus, let's see, that squared would be 49 over 36 plus to the cubed would be, I think, 343 over, what is this, 216, I think? 216 plus dot 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 dot. Huh. These don't seem to be getting smaller, do they? This is like 7/6, a little bit bigger than 1. This is 49/36 a little bit bigger. This is almost 3/2. This is almost 1.5. So these are getting bigger. A sub n is less than a sub n plus 1. Right? My individual terms keep getting bigger, so there's not a chance that this thing converges. So here you go. This one diverges. Right? You gotta always keep your eyes open. These things don't always converge. How about another example? The second dot never works as well as the first. So I'm going to say the sum as n equals 0 to infinity. Can I do that? Can I start at 0 instead of 1? Sure, I can start. I can start wherever I want. N equals 0 in this case. Of 5 over 2 to the n minus 1 over 3 to the n. Right? What does that equal? Well, I know due to some of my rules that the sum of the difference equals the difference, n equals 0 to infinity, and of my first one, 5 over 2 to the n, minus the sum of my second one, n equals 0 to infinity of 1 over 3 to the n. Alright, so I'm going to split these up here. I'm going to work with them individually for a little bit. This one I'm going to call A, and this one I'm going to call B. Alright, so if we work at A first, well, this equals, what's it going to be? 5 over, well, I'm starting at 0. So 5 over 2 to the 0 is 5 over 1 plus 5 over 2 plus 5 over 4 plus dot dot dot. Well, here I recognize this. This is a geometric series. This is really a sub 1 equals 5 and the ratio equals 1/2. So the sum equals 5 over 1 minus 1/2, which really equals 10. Right? And we figured that formula out. That's one of the first things we did. And now if I look at B, that equals, let's see, 1 over 3 to the n this time. So 1 over 3 to the 0 is still, well, that's going to be 1. Plus 1 over 3 to the 1 is 1/3. I just realized this is wrong in my notes, so I have to fix it on the fly. 1/9 plus 1/27 plus whatever. And so a sub 1 equals 1 again. R this time doesn't equal 1/2. We've done a lot of R's equal 1/2, negative 1/2. This time it equals positive 1/3. So S equals, and this time it's 1 over 1 minus 1/3, which equals 1 over 2/3, which equals 3/2. So my total sum equals S sub A minus S sub B, which equals 10 minus 3/2, which is really like 20/2 minus 3/2 equals 17/2. Alright, really pushing the limit of our paper there. But it's electronic paper we could waste, but it's just nice to have it all on one page. Alright, so there's one that converges. We had to use one of our rules. Let's take another look at another example. And what's this one going to look like? How about the sum from, let's pick K. Let's get crazy here. K equals 2. Can I do that? K equals 2? Yeah, I can do that. But it's still going to go to infinity of, now this one's going to get big. I'm going to say 3 over K minus 1 squared minus 3 over k squared, like that. Alright, well, boy, there's nothing really too obvious here about, this one looks like it'll probably be, well, geometric, maybe geometric. No, but it's the number squared. It's not going to be, all right, well, sometimes, it's good just to write these out. So I'm going to say, if I start at 2, this will become 3 over 1 squared, which is just 1. Yeah, get out of there. 1. And then this one will be 3 over k squared, which is 3/4. Is that right? Yeah, okay. And then the next one will be, so I'm going up to 3. So 3 over 3 minus 1 is 2 squared is 4, minus 3 over 9. And with my handwriting, this is going to look a lot alike, so we got to make this a really pretty 9. There. And then the next one is going to be, this is k equals 2, k equals 3, k equals 4. So 4 minus 1 squared, so that's 3/9. And again, I got to make that a pretty 9. Seems like I just did a 9. Minus 3 over, let's see, 2, 3, 4, right? 16. Wait a minute, I'm starting to see a pattern here. When 2, 3, 4, 5, 4 squared is 3/16. Aha! There is definitely a pattern forming here. This is, our old friend, another version of a telescoping series, because all these terms cancel out, right? So we're going to that's going to wind up equaling 3 over 1. Let's see, the last one will be a minus, really, right? So minus 3 over k squared, which equals 3 minus 0, which equals 3. I almost wrote 0, 3. All right, so that one works out. So it's not geometric. We didn't have a nice slick little common ratio and a nice little formula. But if we write out each of these terms, we can see a pattern, and we can do some work with the pattern. All right, the next one I'm going to start on a new page because it's a little bit longer. Oh, great, you guys say. But bear with me, this one's pretty cool. So there's this harmonic series, there's a geometric series, there's all these ones with names on it. This is the one that I'm hoping will get named after me. And this is the not yet famous, I'm going to write that down, the not yet famous, and here I'm going to call it the, someday they'll call it Dressler's how many kids do you have sequence. Ah, nope, it's not a sequence, it's a series. But you'll see in a sec why I got confused. Series. So the other day, someone said, hey, I met this guy, and he's a nice guy, and I said, well, yeah, how many kids do you have? And I told him, and I thought this would be pretty funny. I said, well, I've got 0.8. 8, 8, 8, 8, 8, right? You can see where that goes. So in other words, I told him I have 0.8 repeating children. Now, he didn't think that was very funny, and I don't think he got it. But what was I really saying? I was really saying I have 0 kids, plus, well, this means I've got 8/10ths of a kid, and the next term means I have 8/100ths of a kid, and the next one says I have 8/1000ths of a kid, plus 8/10,000ths, 10,000th, right? And this goes on and on and on and on. Well, yeah, maybe this part here, the 0 definitely doesn't do much for us. But if I just look at that part of it there, this really is a geometric series, isn't it? Because it goes down by a factor of 10 every time. So I could say this is my a sub 1 equals 8/10. And my common ratio here is actually 1/10. Oh, no, that's interesting. So if we plug this into our old trusty formula, and we say S equals A sub 1, which is 8/10, over 1 minus 1/10, right? Well, that equals 8/10 over 9/10. 9. Oh, maybe that's. Sometimes this pen thing kind of smooths things out for me, even though I don't want it smoothed out. So over 9/10, which equals, we flip that guy and multiply, it becomes 8/9 of a child, right? Which means, well, my wife is 8 months pregnant, so 8/9. I keep trying to remind you guys that pretty soon I'm going to disappear and it's going to come all of a sudden, so I hope you don't get too mad at me. So 0.888 repeating also will give you 8/9, right? There's a couple of those in the homework for you guys to try. Holy cow, it's been forever. One more example, and it's some of you guys are saying, "Man, I'm so glad this is over." And, I don't. Well, that's kind of. I didn't mean to do that. Sum with an x, sum of x. No, this is just an example. You thought, well, unfortunately, we're done with trig. Not quite, my friend, not quite. So here's the sum. What if I said the cosine of n pi? Ooh, we're going to sum up all the cosines of n pi over 5 to the n. What about this thing? So I'm going to do a little sidebar here. I think I've got room to do a sidebar. What is this guy? I bet there's probably some tool where I can make this a perfect circle, but I don't know how to use this. I'm going to draw our old friend, the unit circle, and say n pi. All right, now we're going to sum these up. This really equals the cosine. So we're starting at 0, right? We can't always assume we're starting at 1 or 2 or 3. We can start at -1. We can start at -7. It's got to be an integer, though. It can't start at -3.1. So we're starting at 0. So cosine of 0 pi, well, that came up in the quiz corrections the other day. Cosine of 0, it's right here. So let's draw that in another color. How about green? Because we like trig so much. So we're looking at this right here. That's the ray. So the cosine is really the x value of that, or the x value of that. And in this case, that equals 1. So the first term, wow, all this for the first term. 1 over 5 to the 0 is 1. Second term, n equals 2. Cosine of 2 pi. Oh, you know what? I screwed that up, guys. I screwed that up. This n pi, or 0 pi, yeah, 0 pi. So now n equals 1. So 1 pi, where does that go? I'll do that in green again. So this is 0 pi over here. And over here we've got 1 pi. Just plain old pi. So that's pi over there. What's the cosine of this? It's the x value, which is, interestingly enough, whoops, come back. That equals -1 over 5 to the n, well, this time it's 5, plus, next to 0, 1, 2, cosine of 2 pi. Oh, now that's over here. This is also 2 pi. And actually, this is all the even pi's over here, isn't it? So it's going to go plus, now it's going to be this time a 1 over 5 squared, so 25, plus a -1 over 125. Well, even though I've got this cosine, this trig function in here, really I could rewrite this one as simply the sum from 0 to infinity. I've got to start at 1, so I've got to start at 0. I call this -1 to the n, right? Because -1 to the 0 would be 1 over 5 to the n. So isn't that slick that cosine of n pi really equals -1 to the n? I can rewrite that every time. And I know that this is, right, one of the ones, our favorite ones, geometric. So my sum will equal, let's see, 1 over 1 minus my common ratio, which in this case is negative 1/5. So that equals 1 over 6/5. And that equals, flip that guy and multiply, 5/6. Okay, so hopefully that cleared up some of the sequence series issues. Hopefully with that you've got enough to go on to, actually you should be able to pretty much power through the homework given this. So thanks for listening, and we'll see you in class.